So that's pretty great with multiplication. And can I get somebody who has an algorithm that kind of corresponds to this last picture to show us what they did? Some volunteer who did something. Okay, yeah, come on up.
Okay. I don't know if this always works, so you might have to help me. I got really excited. So what I'd like to do is I'd like to think about the patterns involved here. So I'm going to, instead of thinking about each of these as a dot, I'm going to replace each of them with a 23 domino. So here's my post multiplication. So I've replaced each of them with a 23. Okay, cool. But now I have a problem because I have 23 plus 23 here. And I have 23 here. So this is really a 23 and a 46. But I'm not allowed to give you my answer in that format. So I'm going to have some explosions. So I'm going to have 6 here. 4 are going to move over. So I'm going to have 27 and 6. But I'm going to have one more round of explosions. And I'm going to get 2.
That's pretty cool.
Yeah. I think this should always work because what I'm really doing is I'm saying I have 23
You're replacing each dot with 23 dots.
And
You're just replacing each dot with 23 dots.
Yeah.
So you're doing 12 groups of 23, right? You have 23 tens, and you have a group of 23 here and a group of 23 here. Each dot is being replaced by 23 times as many dots. But this way of writing the 23 instead of this way kind of suggests to me like a shortcut to this process.
Oh yeah, you can just expand them inside.
Yeah, that if this line should really be this line, shouldn't it? So when I replace this with a 23, I might draw the picture. So this one dot turns into a 23, and this one dot turns into a 23, and the other one dot turns into a 23.
Oh my goodness.
Yeah, that's awesome.
That's fast.
I missed what you did.
Okay, so Tina's method was to take one dot and turn it into 23 dots and write it this way. But what I'm saying is that this line in here is really between the 1s and the 10s. It really ought to be this line. So I just moved these dominoes over so that this line was here. And same with this line ought to really be here. So I just moved that domino over so that my dominoes lines were the ones already naturally made by my boxes. So I replaced each dot here with a 23 domino straddling the line like this. So that to me is like this algorithm, basically. We're actually really using this domino shape and replacing each dot with a domino as our way of multiplying, which I think is pretty nifty. Yeah. There were a lot of other different approaches. Like we could multiply this by 12 and get basically 24 and 36 and then explode from there. And then we had the like laser beams method. You guys want to draw a picture for us? I think you, do you need another color?
Yes, probably.
How many more colors?
3 colors.
Okay, so red, black, and green would be enough? Here's, all right.
So far, every time I've used this method, I've got the wrong answer.
If you know Tom Lehrer's song, the idea is the important thing, right? Go ahead. So while he's doing this, I think a lot of people started seeing correctly that something like the lattice method is kind of the natural approach here. How many people do lattice multiplication in their schools? Yeah. So you're going to see some version of something like a lattice method here. Oh, you want to, so, okay, so if you don't know the lattice method, this is definitely my 10-year-old's favorite multiplication algorithm by far. So I guess the standard way to do it is like this. Okay, so you do all the multiplications as 2-digit numbers, like 2 times 1 is 2, 2 times 2 is 4, 3 times 1 is 3, 3 times 2 is 6, and then you conveniently have your ones, tens, hundreds, thousands places already lined up for you. So you have 6 ones, 7 tens, 2 hundreds, and no thousands.
Do you always?
Give me another example. A harder one with some carrying, right?
Times 76.
What times 76?
32.
32. 32 times 76. 3 times 7 is 21. 3 times 6 is 18. 2 times 7 is 14. 2 times 6 is 12. I get 2 ones. I have 13 tens, carry the 1. So I have 4 hundreds and 2 thousands. So you're just adding. 8 plus 4 plus 1 made 13 tens, so I had a carry. Yeah. So when you add, you might have to carry, but when you multiply, the carrying is all automatically taken care of. All right.
I think I'm ready to explain.
Okay, there is 23 times 12 with the laser dots.
Yeah, I suspect I may be explaining what you just explained. I'm not sure.
Yeah, but I didn't explain it with laser dots, so it wasn't cool.
Our method of building a machine is you put the machine for the first number at the bottom here. This is just the normal 23 machine. And this is the 12 machine rotated up. And all of the dots become lasers firing. And when the lasers cross, you see black. Colors combust or something. Sort of works.
Where is the 12? I don't see 12. Where is 12?
12 is here. So this is the 2 and this is the 10. So you took the 12 machine, which used to look like
okay, I got it.
2, 1, and rotated it up.
Uh-huh.
So then you get all of these dots, and these ones are sort of 1s, and these ones are sort of 10s, and these ones are sort of 100s. So we built a new machine by cutting it up this way. And so this is this is the right box of the new machine, and this is the second box of the new machine, and this is the third box of the new machine. So this becomes 2, 7, and 6, and I guess there's no need of explosions. One would then start exploding.
When laser beams hit, maybe they.
Well, the original story was there
Yeah.
are different forms of radiation, and these are cancer cells formed when you get zapped by.
So I've seen this
I
called
removed the malicious aspect.
the Japanese method
Japanese method?
of multiplication. Yeah, they teach us in Japanese schools.
They do.
Yeah.
I've heard it called the crossing sticks method because you do it with long sticks, and then you count how many crossings of the sticks you get. So you just take a group of 2 sticks and 3 sticks and 1 stick and 2 sticks, and you lay them out on the table, and then you count. Yeah.